Before we get into the tutorial for today's class, I want to make clear on that you guys understand the fundamental logic things. So if I have a binary number, for example, 11.001, focused. Just a review on logic. If I times 2, what is this doing to this number? Could you give me?
This was binary.
Yeah, binary. To give me the quick answer of it, times 2 is doing what? It's doing what to that number? For example, I have $100 times 10. You know that, right? $1,000. So, or if I get 100.1 times 10, you're getting $1,001. Okay. So in decimal, when you times 10, you are moving the decimal point to the right. And if you divide by 10, you are moving the decimal point to the left. But in binary, you times 2, you move the binary point to the right. If you divide by 2, you move the point to the left. Okay. All right. And if this is a 2's complement, what is 2's complement? Do you remember it? So it's a signed number, right? It's a signed binary. And if I have 5 in 2's complement, what is 5? We are saying 1, 0, 0, 1, 4, 1, 5. In 2's complement, it's not 5. So in 2's complement, what is this number? This one is not 4 anymore, but instead it's minus 4. In 2's complement, it's minus 4. So we just need a way to represent negative numbers. That's how they define all the rules. You know, this one must be minus 4. So the MSB here must be minus 4. And then you got a 1, so it's minus 4 plus 1, you're getting minus 3. So this number in 2's complement is not 5. It's minus 3. So if you need a 5, you need one more bit in the memory to hold a 0 in the front. So you're getting a positive number because the first bit is not 1 anymore, it's 0, which means it's a positive number instead of a negative number. So this is what is this number in 2's complement? Yeah. So what is this in 2's complement? Seriously? You know that, Cheyenne. You need some time to recall that memory. Yeah.
He increased 2 to 5. Come on. Technically, negative 33. Oh wait, negative 31.
That's right.
Negative 2?
Mm-mm.
Negative 1.
Mm-mm.
What? 0. 2. Oh, 2. 2 to 2, negative 4.
Mm-hmm.
Negative 4. plus what, -3.
Are we in two?
Yes. This is 2's complement, because the 1 in front makes it.
Okay, next
But
number.
if we put a 0 in front, then we're in 2. We just did that.
Well, but why is the 1001 -3 also?
1, 0, 0, 1.
Why
No,
don't you do
where?
it?
-4, and then plus 1.
Oh,
Yeah, didn't you just do the same thing with 101 somehow?
That's a good point. Yeah, wait.
That's why I was kind of
oh,
I was right. It was
oh, yeah. Sorry.
okay. Just want to make.
Good catch.
okay.
Yes.
Okay.
So what about this one? 1101. What about that? -8, 4, 1.
Okay.
It's not changing the number. Keep in mind the negative 2's complement numbers. You can add a million ones in the front. It's not changing it.
Oh. Okay. How do you know when?
Jesus told me.
What?
I knew it.
It all makes sense.
Let's see.
Now.
So let's pick up binary, okay? No, let's do decimal. I'm pretty sure it's going to show binary. Are they going to do that? Show me. So if no, let's do decimal. I'm trying to find, so let me know what is -2 in 2's complement. What is -2? -2 is this, right? It's -2. It should be -2, -2, -2, -2. It's going to be -2 forever. Let's try it. So -2. Let's use 2 minus 4. Look at it. Why does it don't show more? How many are there? How many bits are there? 64. Why? Yes, it's a 64-bit CPU, the Intel i5, or yeah, Core i5, 7th generation. It's a 64-bit memory system. Okay. Anything else I want to show you before we move forward? Okay, let's get into the tutorial. Okay, today's tasks. Let me clear on that first. What we are going to do. Okay, so I need 2 lectures to cover the materials in this website, web page. It's gonna be today and next Tuesday. And today I will just do a probably 20-30 minutes explanation to the floating point and fixed point representations. And then I'm gonna give you the time to work on. So before you leave, you should finish task 1, 2. No, task 1 and 2. Yes. And on Tuesday, we're going to work on number 3, number 4. Okay, let's try to finish most of them during the class, so we have a lot of time in the class. If you couldn't finish it, you can use that as homework assignment later, right? And I'm going to do introduction for about 10 to 20 minutes, and we will do the quiz on GVim. Are ready for that? Pretty much?
Yeah.
If you're not ready, if you didn't do well, I'm going to do another quiz later. Until you are ready. Stop being so mean. Okay. So look at the number system in the computer systems. I got a PDF file, from the textbook. Did you buy the textbook? It's going to be intensively used in the semester. Yeah, 2 of them. The first one covers probably 80% of the materials in this class, and 20% is for the other one. The second one is for the soft core. It's the SOC. So actually, the second textbook is it's actually higher quality and more recognized in the field or in the university systems. The first one is just very practical and very simple, straightforward. It's easier to access and understand. So that's why I prefer the first one to cover most of the materials in the class. The second one covers some more advanced topics like the software core, which have to use the second one. The first one didn't cover that. So FPGA for the fundamental applications is very simple. Just you program in Verilog. You can do a sequential logic, combinational logic. It's very simple. I have done that. But actually, in industry, it's a bigger industry or higher demand to hire FPGA engineers compared to pure IC engineers. Not every company can afford that. You can count it who are doing really doing these IC tape outs. Not too many. Samsung, Qualcomm, Broadcom, there are many other ones you probably don't know their names, but not too many. Compared to the number of the companies that are doing FPGA flow, it's actually a lot more in there. So there's a way higher demand to do the FPGA flow, which is I think exactly what the guys in the senior sem are doing. So the FPGA flow, you're going to learn it starting from this one, right? So after you learn all these combination protocols and sequential logic, the basics, the FPGAs, and we are going to move forward with software core here, and there will be a lab associated with it. So you are actually making out a microcontroller from the FPGA board you have. Is that awesome? So the FPGA chip, you put a core in there. Definitely you didn't program the core. You use a core from it's open source core and put it in the FPGA and put the ports in there, and then you program it using assembly and make it work as a microcontroller. It can display numbers, send data through serial to your desktop, or can blink LEDs like Arduino board. It won't be as powerful as Arduino's, but very similar. So as long as you know how to make an SoC on the FPGA by taking this class, and in the future you can use the same concept and embed. That's why it's called embedded systems. It's embedding all these intelligent cores or digital circuits into the chip to implement some functions. And in the future, there are all the other types of cores, like the 6502 core, the senior SAM team are working on right now from 1980s, right? They're still being used. And there's a more advanced core from Xilinx. It's called microblaze and not picoblaze. So picoblaze is the smallest, simplest core, and there's another one. It's called microblaze. There's more functions in there, more instructions for that CPU. And then in the future, you can implement RISC-V, which is the most popular right now. Is maybe in the future will take over ARM's share in the industry. And no, for now it's still not, but in the future, who knows? If Google acquire it, trying to like Android, right? If Google invest into it, in the future it's going to be dominant. It's going to dominate the field. And RISC-V is another one, and you can, if you work for another company making smartphones or tablets, it's going to be ARM, which is the most popular, the most powerful ones for now on this planet. So it's a very similar concept. It's just putting cores in there, putting the communication protocol supports, UART, SPI, I2C, place them, alongside with the cores into the CPU, into the chip, and just make it work and connect them with all the logic gates. Okay. Let's come back to the tutorial. The first one is very simple, unsigned UQ 16.16 data type. Just 16 bits, 16 bits. It has a fractional part of it, because the integer has 4 hex numbers or 16 binary numbers. For the fractional part, it also has the same number of bits. And for short, you have to understand hex, right? So every 4 bit, you can represent it by 1 bit hex number. So we're getting 000E, 000E. It's 2 in hex and 000, 2, 0, 0, 0. Okay. For signed UQ15 for this specific format or standard, you have to put a 1 in the front. It's not two's complement yet. It's not 2's complement. It just simply put a 1 in the front to represent a negative sign. It's like a bar in the front, but you just put it vertically. That's the only thing you have in the can be set in the memory system. It's the 1 and zeros, right? Just put a 1 in there to represent the negative sign. So this is negative 14, but why is UQ 15? Oh, because the numbers are 15 bits. MSB is a sign bit. I'll have 15 bits for the number. That's UQ 15. And it's a signed UQ 15. Okay? You just need to know there's a format called that. Okay? You don't have to memorize it. I don't believe that during the interviews they're going to ask you to write down the number in the UQ 15 system, in the UQ 16.16 system. No, they won't. But they will ask you to program a state machine using Verilog. It's very likely. For the NVIDIA, NVIDIA is making all the chips for the GPU boards, right, for the computers, NVIDIA. It's one of the most powerful, richest company right now in the world. And NVIDIA's interview, it's just a handwriting code on paper. I saw that when I was in the interview in UCLA many years ago, and it's just a very big lobby, and there are different kind of companies like NVIDIA, Broadcom, and TI. So you can see NVIDIA has a super long line because they pay them really well. So the people are taking the line to taking that interview, and they probably can have maybe 10 students at one time to take the interview, and then another 10 in the line. So they grab 10 and give them the paper and show them a state machine, just write it down in Verilog. Yeah. There are so many companies are asking the skill sets in hardware design. Not really C language and Arduinos, but mostly FPGA, because they need the people to design all the ASICs. But there are also a lot of companies are asking, microcontroller skill set, PCBs. But compared to ASIC design and FPGAs, the microcontroller level is a little bit more undergraduate level. That's why you guys learn Arduino in your M&I before you learn logic. You start playing with Arduino, then you can see high schoolers are playing with Arduinos, but not FPGAs. Rarely FPGAs. They don't understand logic, so they couldn't do it. So FPGA is more popular, more important, but sadly, we only have 4 students registered. Yeah. Getting to college, learn something useful, right? Learn the most important things. Okay. UQ 15 and UQ 15.16 is assigned, and you got 15 digits for the number, and fractional part you got 16 bits for the number. And you can write it down in hex form. It's easier to represent it. And now floating point. It's something new to you guys. I've heard about it, but you never know how it's being represented in the hardware. I've learned in C++, I believe. But how it's being represented in the hardware. So look at this. So the number is being represented as the -1 to the s power, and then 2 to the e power, so the e is exponent, and times f. F is a fractional part of it. So here's a way to convert it. For example, let's just look at examples. And again, so the floating point numbers are represented as SEF in the computer system, which is SEF, but not the number itself. Keep in mind. And how do you get SEF? Because we know we want to represent the number, and they are SEF in the memory system. And now we need to find SEF. Make sense? So here's a number, for example, and let's find out SEF of this number. So first I have to convert it into binary. So this is a decimal number, and let's convert it into binary. It's this. Okay? And you have to move the point, the binary point, to the left by 3 times in this case. So I only have 1 digit on the left as an integer. So you move it by 3 times to the left, which means you divide that number by 8. 2, right? So I have to, multiply that number back to recover it. That's why you convert it into 1 point, you move the point here, it becomes 1 point something, like 1 point something, right? You have to times 8. So you're not making a wrong number. Make sense? And S is sign, it's a sign bit. If this is a positive number, so the sign should be 0, which makes sense because you got a -1 to the 0's power, it becomes 1. So it's not changing the number, it's a positive number. Otherwise, you got a 1 here, it becomes a -1, right? So you are getting a negative number. So now it's a positive number, so S must be 0. Okay? So you got S by far. So how do we got E? So the E, keep in mind, since you moved that digit, oh, E is over here. It is 2 to the how many times power? You know what I mean? You moved over to the left by 3 times, right? Have to times 2 to the something power, right? And that number is the exponent is the number here. And the rule is I have to add it to an offset, which is 15 by this number system. I will let you know why. But now just remember that, right? So 3 is the exponent, and you have to add it to the offset, which is, or it's called bias, which is 15. So I have to add to 15 in this half precision format of the floating point number system. Don't make it complicated. Just remember we are not using other precision format in this class. Just it's good enough if you know what is a half precision format. Okay, so we're always adding 15 to it. I'm going to show you why later. Okay, so for E, so we need to know SEF, and now we got E, and now we got S, and now we got E as well. So E is this number plus 15. And that's a decimal number. I have to convert into binary. Make sense? So F is very simple. F is just everything here after the binary point. But I have to make it up into a 10-digit binary number in this precision format. Okay, I'll let you guys go through it one more time in your mind. How do we get S? If it's negative, then put a 1. If it's positive, yes. Okay. For E.
Don't know where the 15 comes from, but it's just there.
That's a very honest answer.
And then we have the exponent that we had.
Yes. Okay. What is F? No. Binary. Binary point.
Yeah.
Yeah.
I mean, like
the point.
Yeah. That's what I mean. But it does.
Yeah. So the goal is you have to form a 10-bit binary number for F. So if you don't have enough number of bits, for example, here, how many bits do you have? For F, 6. It requires 10-bit number. Add 4 bits to it. Is it going to change the number or not? No. You're not changing the number by adding trailing zeros in the fractional number, right? So it's fine. So what if you got 11 bits you're writing? Are you trying to add more zeros to it to make a 10-bit? No, you got more already. What you should do? Ignore the last one. It's less precise. You couldn't get the perfect precision, right? Just ignore it.
Half precision.
Yeah, half precision. Yeah. So you only have 10 bits of precision there. Okay, make sense? Okay. Now let's look at the negative number. So now we combine them, okay? Here's S, no problem. Here's E, no problem. E is here, right? See, 18. And here's F. We just added 4 trailing zeros to make up the 10-bit for F. But you have to regroup them because you need 4 bits for the hex numbers, right? So group and group like that, right? So that's how I regroup them. And then eventually you'll find a hex number for it. It's going to be 4B10. Okay, you don't have to do the calculations again, but if I ask you to find negative 14.125, find its floating point number in half precision format, what's the only difference? So I'm going to put a 1 in the front, so the only difference is S. Right? What about this one? Oops, you couldn't move it. You got nothing in the integer part. But it still should get a 1 in the integer spot.
Why is it
So,
minus? Oh, it's because.
so this number you convert into a binary number is 0.001, right? And now we need a 1 to be at the integer part, that spot. So I have to move this one, move the point to the right by 3 times. So that's why I have to use 1.0 times 2 to the negative 3, the third power, to make it happen. That's why you need a bias, because if you don't have a bias here or offside, when you're trying to minus something, you wouldn't be able to do it. So have something to subtract from, right? Okay. Now you got a S to be 0 because it's a positive number, right? And then E becomes 15 minus 3, right? And you convert into binary. It has to be 5 bits. Keep in mind, E has to be 5 bits. E has to be 5 bits. Okay, and F, you got nothing in F, just all zeros, just 10 zeros. And then combine them, okay, and then regroup them. And here's a floating ICF, or floating point representation of that number. Can verify it. Here's a link of the online calculator, but don't do it for the homework assignments. Show the process to get credit, okay? Float toy. Use a half precision 16-bit format. I can see 0.125 gives you a hex number of 3000. That's what we got. Okay. Example 4. Find out the half precision format of the floating point representation of this number. So convert into binary first. You don't have to do it by hand. It's a lot of pain in there. So convert it into binary. Here's a binary number of it. One more question. Are we considering 2's complement by doing this? By far, no. No. Professor, you tell me the rules, okay? Whenever you want to use 2's complement, just use it. Whenever you are not using, we are not using it. It's okay. Just, yeah. Pay her the bill. I parked it in Aztec. $30 a month.
30?
Yeah, it's fine. It's way better than like whatever you got here, like $85 a month. Yeah. Yeah, actually I drive there. I mean, my truck, like, round trip is 1 hour is probably $10, $15, $20, I think. I don't know, maybe not that much. Maybe $10 gas. Awful. Yeah. All right. Okay, convert into binary first. You can see it's pretty long, right? It's not the ideal numbers I have been giving given you guys as examples like 0.125, 0.25, 0.5 are pretty sweet numbers to be converted into binary, but this is not sweet. So that's why, please use a calculator, okay? So you got this one. You don't want to do it by hand. So you got these many bits for the fractional part. And now, let me know, okay? I want to hide it for now, okay? So what is S? Yeah. What is E?
1.
1. That 1?
Or no, 0.
No, 1. You have to move this point to the left,
Oh, I was looking at 3 point. I'm sorry.
right? You have to do the operation has to be done to the binary numbers, not the decimal. I have to convert into binary first. So you move this point to the left, so you have to times 2 to the first order power, right? The first power. So E is 1. What is F? Starting from here, all these numbers, right? Yeah, that's right. Yeah. Just use 10 of them. Starting from here, right? Count 10. Starting from where? Yes. Yeah. Just testing, guys. Good catch, actually. Okay. So you can see there are different formats. I know you don't want to go through all the different formats, right? Do you? We'll just learn half, okay? As long as you know how it works. So there are all different ones, right? We just went through the half precision. It's defined by the IEEE 7454 standard or something, right? Okay, so the half precision, what we just learned, has a bias of 15 bits, right? And 1 bit for S, and 5 bits for E, and 10 bits for F. So total is a 16-bit floating point format. 16 point. So we're expecting 4 hex numbers. That's why we're getting like 3000 because it's 4 hex numbers, 4 bit of hex numbers. Make sense?
Yeah, but where did they?
Mm-hmm.
Where did they get the They just randomly come up with it.
Yeah, you must find.
Rest and then had to get 6432 or whatever.
I think so. If you do a calculation, it must make sense. I think you are having 5 bits for E, right? So if you get the most negative number we can get from the 5 bits is going to be negative 16. Wait, 5 bits. Yeah, negative 16.
32?
Are you able to do that? I don't know, but negative 16 is bigger than 15, right? If you add it 1, it's going to be a minus 1. So I think probably the largest you can get is negative 15 or something for 5 bits. That's why it has to be positive enough, or you need like 15 positive binary bits in there in order to compensate that. So you're not getting negative numbers for E. Yeah. So the addition's straightforward. Floating point addition, you need to be aware of here. How to do additions for them. So the rule of thumb here is you have to have the same number of exponent first before you do the additions. You don't want to convert them into like 1 point something for the 2 numbers. They have different number of digits for the integers. Right? So you have to convert them into the same exponent first, and then do the addition, and then find a result, and then start from there. So for example, I converted them in. So I have the same exponent first, and then add them together. Okay, so here's the result of the addition, and then I start from there. Did you get it? So when you have to make the correct result from the result of the addition before do too many conversions for the two numbers. You have to make sure the result is right, no matter what kind of format you are using. So this is the right result, okay? And then I start from there, and I move the point to the left for 2 more digits. So I got the 5, okay? And then I start from there to get the S, E, and F from here, okay? And these are two's complement being implemented, since the professor just told you to do two's complement, and now you use two's complement. Okay, just read through it. So subtraction, you can use addition, you're adding a negative number instead of do a subtraction in the computer systems, right? So this 39.375 is this guy, right? And then the negative 14.125 is this guy, okay? So subtracting that one is same as adding a negative of that one, okay? And now I just need to convert that negative number to its complement instead of having a negative sign in the front, because memory systems are just transistor or D flip-flops are holding, binary numbers but not holding signs. So that's why I have to use a two's complement to represent negative numbers, okay? And so I have to convert this one to its two's complement. And when we do that, what I showed you here is I convert the integer part and fractional part individually to its two's complement and adding them together. Because the two's complement of this one is, see, negative this guy equals negative this plus negative 0.0010, no problem, right? Okay, and then I convert its two's complement here and here individually. Okay, this is two's complement for this one, and this is two's complement for this one. How do you find it? How do you find the two's complement for these numbers? I have to understand what is two's complement first. Okay, so I just showed you how that works. The MSB is a negative number instead of positive, and then adding all these positive numbers to it to get the real number. So that's why. But also, if you have a number like that, there's another way to do it. So this is depends on which way is better. Okay, so I have told you that if you have a two's complement number here, okay, how do you figure out what is that actual decimal number? So you find out this is -8, this is 4, this is 1, so you know that it is -3, right? Okay, it's -3. That's how I figure it out. But however, if I'm asking you to convert, so this is +5, so you know this is +5, right? And I'm asking you to find out -5 from this. How to do it? Definitely you can think about, hey, -5, I need a -8 first, and then I need a 3, right? Okay? Or another way to do it is you add a 1, you invert every bit and add a 1 to it. It just works out. Don't ask me why, but it just works out. So that's how you convert a positive number to its negative number. Invert. You learned in logic, you just forgot it. Invert each bit, and then add a 1 to it. That's a process of converting a positive binary number to its negative counterpart. So, for example, 0101 is +5, right? Now let's invert it. 1010 and +1. 1011. Is that -5? Yes. -8 plus 3, right? It just works out. It just works. So you can just switching between these two methods, when you are dealing with two's complement, it just depends on which one is easier for you guys to do. So for example, the negative number here, okay? It already shows you the binary number and how to find out the two's complement of its negative counterpart. Which way is better? We want to use the Dr. Lee's method or the textbook method. So which one is Dr. Lee's method? The one that you find out the MSB and you're adding it to the positive numbers. This is pretty much not covering the textbooks, right? But this is always covering the textbooks, but never tells you why. And I didn't tell you why as well. So I didn't know why. I learned from the textbook. Invert it and add a 1 to it, you're getting the two's complement. Why? You're not deserved the answer. Nobody will answer that. No professor will answer that for you if you're attending other institutions. So it's just, if you dig into it, just look at the paper and think about it, you probably will find the answer. Why it works, you don't have to. Okay? The textbook method here is invert each bit and add a 1 to it, right? But my method is find the MSB first and adding to it. But for this case, which way is better? To find out negative of this, I don't even know what is this number. Yes, I can tell. 14, right? I can calculate it. But what if they have more ones in the front? And you couldn't even tell what is that number, right? Mm-hmm. And they are finding the MSB, I'm adding something to it, I make it negative. You have to do a lot of calculations. So in this case, to find out the two's complement, what's the better way to do it? Yeah, invert. The textbook method is better, right? So invert each bit and add a 1 to it, and it's going to be the two's complement counterpart of it. Okay, so you can find out, this. See, I invert these 4 bit, I got 4 ones, right? And I invert these ones, I got 0, 0, 0, 1, but I add a 1 to it, that's why it's carrying out. So it's getting 0, 0, 1, 0. You can find out two's complement in probably 2 seconds by using the inverting method. If you use my method, it takes like 1 minute, probably, okay? And so now this part, the integer part is done, and let's look at the fractional part. How to convert a fractional number into its two's complement. Invert every bit and add a 1 to it.
Yeah, that totally.
Yeah. Where are these ones? Where does this come from? Hey, it's a 0.0010. I just didn't show it, right? It has many zeros in the front. It's like 0.0000. Depends on how many memory bits are in there. So when you are inverting everything, you have to invert the ones as well. They exist. You cannot ignore them. Make sense?
Oh, yeah.
Right?
Yeah.
Okay. Make sense? Okay. And then I add a 1 to it, so that's how I got this number here. All right. Add a 1 to the LSB. Because all the zeros are converted to ones, no problem here, right? And then this becomes 1101, right? 1101, you add a 1 to it, it becomes 1110. Complicated. You're doing all the job the computer is doing every day. So you have to force your brain to do all the whatever the CPU is doing. Actually, our brain is more powerful. I think we can do analog, we can do digital. They can only do digital. You can tell 1, 2, 3, 4, 5.
Sometimes the 5 looks like S.
Okay, and the rest of these number systems are pretty straightforward, and we are not even doing too much multiplications and division. I think it's just put it there. And ASCII code, I got to know it's called ASCII, pronounced as ASCII instead of ASC2. I learned in China when I was in college, like all the professors like ASC2 code, ASC2 code. But you never heard about that, right? Just ASCII?
Yeah, just I know it's a French.
Yeah. All right, embarrassing. ASCII code, and it's just a 8-bit binary number or 2-bit hex number. If I'm asking you to, you guys, it's just an encoding system. It's coding up all the symbols on the keyboard to a hex number. So this is very useful to learn it right now because we're going to do the keyboard USB communication to the IPGA later this semester. So you need to know what are these numbers. If you press the key on the keyboard, it's going to send the ASCII code to the computer. And what is that code? So if you look at the table, you can find out. So for the email, the @ symbol, you want to let me know what is that ASCII code for that symbol?
4.
No, for 0. See, MSB, I told you MSB on the.
Yeah.
So MSB, this is MSB for the hex number. So it must be come first, right? So it's before 0. So what is G? George, G.
4, 7.
Yeah. That's it. And things. There's some examples, about examples, but you don't have to work on it if you don't have time. And so this, I know this is a, wait, when this is due, I haven't assigned a, no. It's gonna be next Thursday, right? It's gonna be next Thursday, since we have a new lecture on next Thursday. So you can start working on it if you like. These are just combinational blocks. Okay. Trust me, simple, very simple. These are, that already shows you how to do it. You just need to go through it and do it, okay? And you have the time in the lab today to work on the lab and also this one, okay? And I'll help you if you have any questions. Okay, we should have the time to do the quiz today. And I'm expecting you guys to finish these tasks by the end of the week or today. I don't know, depends on your schedule. So at least starting from Monday, you should work on this one, but you don't have to submit them separately. It's just one report due next Thursday by the end of the day. Right. Okay. Let's do the quiz. You want to do it on the laptop or?
Yeah, because I can't get Gmail to work